Okay, so now we want to take our matrix equation solving skills a step further and apply them to simultaneous linear equations. So previously, and in the notes here it says in the Matrices 1 booklet, but actually I now give you just one booklet. So in this booklet, earlier in this booklet, sorry I should say, we looked at how we can represent a system of simultaneous equations using a matrix equation. And that was all we did. We just looked at how can we write those simultaneous equations as a matrix equation. And we saw that essentially it was this. So you want to make sure your equations are lined up in the same format. So you want to make sure that you have x terms first and then y terms, or if there are different letters that's fine, but just make sure that the like terms are lined up and then that they're equal to our constant values. And then it's very easy to change it into the matrix equation. The 2 by 2 matrix becomes the 4 coefficients. Okay, so in this case we have positive 3, positive 2, positive 4, and negative 1. That's how we get that 2 by 2 matrix. Multiplied by x times y, or whatever letters they are. If this is t and v, it'll be t and v. Okay, as long as you've got both equations in the same order. And then equal to the just the numbers on the other side in a 2 by 1 matrix. Okay. If you had a third equation, obviously you'd have 3 by 3s and 3 by 1s and x, y, and z. And again, like these give the matrix equation because these give the simultaneous equations because if you were to multiply that pair of matrices on the left out, you do row times column, which would give you 3x plus 2y. And you do row times column, which would give you 4x plus or negative 1y, so minus 1y, so minus y, and then that's equal to 18, 13. And if these two matrices are equal to each other, the only way they're equal is if that thing equals, if that thing equals that thing, or if that thing equals that thing. Okay, and so there's your two simultaneous equations. Alright, so we want to be able to sort of create the matrix equation though, so we're looking at from this, taking the 4 coefficients, so you get your matrix of coefficients multiplied by your variables equal your constant values on the right hand side of your equations. Now if we think about this matrix equation, we're interested in solving for that. Okay, so we can think about this as being A times X equals B. A matrix times another matrix that we want to solve for equals another matrix. And in the previous video we talked about how to solve these kind of matrices. Okay, so we know that we want to use the inverse matrix. We want to do the inverse of A. We want to pre-multiply by the inverse of A to cancel that A out from there. And so we pre-multiply by the inverse of A over here. And so ultimately we find that X is equal to the inverse of A times B. So in terms of solving our simultaneous equations up here, we're going to need the inverse of that matrix, and then we multiply that by that matrix. And so we can get our CAS to do that for us. The inverse of that times that will give us our two answers, which are 4, 3, or we can find our inverse by hand and do the multiplication by hand. Now, your CAS cannot solve the matrix equation. You can't type into your CAS, you can't type this matrix equation into your CAS and say solve for x and y. Okay, so you need to do this, be able to do this manipulation by yourself. So you need to be able to work out that this is what x is actually equal to, and then your CAS isn't solving it, it's just working out what that's actually equal to. So your CAS can help you, you don't need to do this whole thing by hand, but you do need to be able to rearrange the equations to get x on their own by hand. And then once the matrix xy is equal to 4, 3, that tells us that x has to equal 4 and y has to equal 3. Okay, so let's have a look at this process. So we want to use a matrix method to solve, actually before we move on from that, the other thing I would say to you though, if the question is essentially solve these pair of simultaneous equations, and you've got your CAS, which you always have in Further Maths, you wouldn't use a matrix method unless there was some way of them forcing you to do it. Like in the next example where we actually need to write out the user matrix method, so we need to write out the steps, okay, the matrix steps. If the question was just solve this pair of simultaneous equations, you wouldn't use a matrix method with your CAS. You would just get your CAS to solve simultaneous equations, which is menu 3 for algebra, 7 for solve system of equations, and then I just always choose 1. 2 would work in this instance as well, but I would just always choose 1. So menu 371, solve system of equations. Here we have a system of 2 equations, and the variables in those 2 equations are x and y, so we don't need to change anything in there. and then we simply enter our two equations in here. 3x plus 2y equals 18, and 4x minus y equals 13. Press enter, and it tells us straight away that x is equal to 4 and y is equal to 3. Okay, so if you're not being explicitly asked to sort of write out the matrix equation or show how the matrix equation can be solved or whatever it might be, you just need to solve the simultaneous equations, then I wouldn't go near matrices. I'd just get my CAS to solve the simultaneous equations, menu 371. Okay, let's have a look at some examples. Let's focus on using the matrix method in this instance. So once again, this is sort of a technique that is useful if you've got 10 equations with 10 unknowns. Okay, set up a matrix equation, get your computer, or in our case CAS, to solve it. However, you know, 2 equations in 2 unknowns, there are plenty of other ways we can solve those simultaneously. But for here, we want to have a look at how we use the matrix method. So use the matrix method to solve the simultaneous equation. So let's first of all change these simultaneous equations into a matrix equation. So we're going to get a 2 by 2 matrix, which is made up of the coefficients. So the first thing I check is that my x terms are lined up, my y terms are lined up, my constants are on the other side. So my matrix of coefficients in this instance is positive 2, positive 3, positive 3, and positive 5. And that's been multiplied by x, y. So if we were to expand that out, that would give us the left-hand side, 2x plus 3y and 3x plus 5y. And then that's equal to 2, 2. Okay, so let's think about this as a times x equals b. Okay, so what we're going to need to do to solve this is pre-multiply by the inverse matrix, so that gives us I, and so we're just left with x is equal to the inverse of a times b. So that is the inverse of a, so the inverse of that times that. And we can get our CAS to work that out for us. So let's go with a 2 by 2 matrix. So it is 2, 3, 3, 5. And we want the inverse of that, so the power of negative 1. And we want to multiply that by a 2 by 1 matrix, which has 2 and 2 in it. And so we get 4 and negative 2, and so therefore x is equal to 4 and y is equal to negative 2. Okay, consider the following sets of simultaneous equations. Okay, so this set here, we turn it into a matrix equation. It looks like that. We solve that matrix equation by taking the inverse of, multiplying by the inverse of this, pre-multiplying by the inverse of this, and so we would need to find the inverse of 2, 1, 6, 3. The problem is, in this particular set of simultaneous equations, when we do that, when we try to find the inverse, we see that the determinant actually equals 0. And so that matrix of coefficients is actually a singular matrix, which means that we're not going to be able to solve this matrix equation, okay, because we can't find the inverse. And the same thing happens. I'll go down to the graphs in a I'll continue. So what we'll see here is when this happens, if we were to think about the graphs of these two lines, if we were to graph 2x plus y equals 4 and 6x plus 3y equals 10, we would actually see that these two lines are parallel lines. And so when we're solving simultaneous equations, what we're finding is the coordinates of the points where the line, or the point where the lines cross. And so if the lines don't cross at all, we're not going to get a solution. So that's why it made sense that the determinant was equal to 0. In the second example over here on the right hand side, we've got our simultaneous equations. We can convert them to a matrix equation in this way. We're going to need to pre-multiply by the inverse of that to solve it. So we're going to have inverse of that times 515. And again, in order to work out this, we're going to need to find the inverse of 1339. And when we do that, again, we find that the determinant is 0. And so therefore the coefficient matrix is a singular matrix. And so we can't solve the matrix equation. If we look graphically at what's happening here, what we're actually seeing is these are actually the same line. If you draw x plus 3y equals 5 and 3x plus 9y equals 15, they're actually the same line. And that's because if I take this whole equation and multiply it by 3, I get this equation. So they're actually exactly the same equation. So there's not just one point of intersection there, there's infinitely many points of intersection. And again, we get this determinant will equal 0 if we try and solve that. So when we get a matrix equation that represents simultaneous equations, where we cannot solve it because we find we have a singular matrix, that's indicating one of two graphical things are happening. Either the two lines are parallel and there are no solutions, or the two lines are the same line and there are infinitely many solutions. Now, in further maths, we're not going to need to make that distinction. We want to group these together to say if the determinant is equal to 0, hence there's a singular matrix and we cannot solve the matrix equation, that simply tells us that the two equations do not have a unique solution. They might have infinitely many solutions, but they do not have a unique solution. There's not a single solution. There's not one point of intersection. So that would be the statement we would make. If we're trying to solve simultaneous equations, we find that the determinant of the coefficient matrix is 0, then we would say that those simultaneous equations do not have a unique solution. Okay? And so that's summarised here in the table below. So any system of linear equations can be represented by a matrix equation of this form, A times X equals B. If A is a regular matrix, so that is it does have an inverse, then the simultaneous equations have a unique solution, and we can find it by working out X equals the inverse of A times B. If A is a singular matrix, that is that the determinant of A is 0, then the simultaneous equations do not have a unique solution, and that's what we would write. There is no unique solution. Okay, so determine which of the following pairs of simultaneous linear equations have a unique solution. Okay, so if we were to set up the matrix equation here, we would have, so first of all checking we've got our x's and y's lined up and our constants on the other side. So then we extract our coefficient matrix, so 2, 2, negative 3, 1, times xy equals negative 4, 14. In order to solve this, we would need to use the inverse of 2, 2, 3, 1, the inverse of that. And so therefore, if we're going to find the inverse of that, we would calculate its determinant. Sorry. So we're going to calculate the determinant, which is going to be 2 times 1 minus 2 times 3, which is 2 minus 6, which is negative 4. And so therefore, in this case, a unique solution exists. Because, so I'm just going to make all of that a bit smaller because I've drawn a bit big and haven't got room now. Let's just do that. So we really just need to think about the determinant. In this instance, the determinant is non-zero, and so therefore there will be an inverse matrix, and so therefore we will actually be able to work out what this answer is here. Okay, the unique solution is whatever we get when we do that multiplication. Okay, alright, so we really just need to focus on the determinant of the matrix of coefficients. Okay, so this matrix equation here, again we've got our x's and y's lined up, so we get 1, so 1x, negative 3y, negative 2x, 6y, times xy equals 412. So we really just want to focus on the determinant of that, which is 1 times 6 minus 3 times minus 2, so that's 6 minus 6, which is 0. Okay, so this one, no unique solution exists, because we cannot find the inverse of that matrix, and so therefore we cannot solve the matrix equation. Now, there might be no solutions, or there might be infinitely many solutions. We don't know that, and we don't need to make that decision in further maths. We just need to know that there will not be a unique solution to this equation, okay, if the determinant equals 0. Alright, and then if we think about this third pair of simultaneous equations, so we're going to get, again, x's and y's are lined up. So our coefficient matrix is 3, 5, negative 6, and negative 10, times xy equals negative 11 and 22. So we're really just focused on whether or not the determinant of that is 0. Determinant is 3 times negative 10 minus 5 times negative 6. So that is negative 30 minus negative 30. So it's negative 30 plus 30, which is 0. And so therefore, again, determinant doesn't exist, and so the inverse doesn't exist, and so the equation will have no unique solution. So the simultaneous equations don't have solutions. Or sorry, they might have solutions, but there might be infinitely many of them. So they do not have a unique solution. Okay, example 3 here. Let's set up and solve a matrix equation to solve the following system of equations. Okay, so again, if it didn't specify about setting up and solving a matrix equation, I would just use my CAS to solve the equations simultaneously. So we've got 3 variables and 3 unknowns, so it's going to be a 3 by 3 coefficient matrix. So what you want to think about for this equation, it doesn't have 3 terms in it. I want to think about that as being 3x minus y plus 0z equals negative 3. Okay, and then I've got my x terms, my y terms, and my z terms all in the right order, and my constants on the other side. So the coefficient matrix this time will be 3 by 3. So it is 2, 1, 4 from the top equation, and then it is 3, negative 1, 0 from the middle equation, and 1, 4, 5 from the bottom equation. They are being multiplied by x, y, and z to create the left-hand side of those 3 simultaneous equations, and then they will be equal to 17, negative 3, and 7. Okay, so there's my matrix equation. Now I know if I've got A times X equals B, I need to pre-multiply by the inverse in order to get rid of A from this side of the equation. So I know that X is the inverse of A times B, which in this case is going to be the inverse of 2, 1, 4, 3, negative 1, 0, 1, 4, 5. So it's the inverse of that multiplied by 17, negative 3, 7. And so I can get my CAS to work out, to do that matrix multiplication for me. So I'm going to get my 3 by 3 matrix. It's 2, 1, 4, 3, negative 1, 0, 1, 4, and 5. We want the inverse of that, and we're going to multiply by, now we need a 3 by 1 matrix, so 17, negative 3, and 7. Okay, so we get negative 10 on 3, negative 7, so I'm just going to write that a bit more clearly, negative 10 on 3, negative 7, and 23 on 3. And so therefore, x is equal to negative 10 on 3, y is equal to negative 7, and z is equal to 23 on 3. Now, once again, with your CAS, you need to write, we need to see this line here. So we need to see this, that's how you use the matrix equation to answer this question. If the question says set up and solve a matrix equation. We've set up the equation, we've solved it, okay, by showing that we need to do the inverse times, the inverse of the coefficient matrix times the other matrix. But there would be nothing to stop you if you wanted to, at this point, in order to, in the end, find the answers. There will be absolutely nothing to stop you, just let me get rid of that, solving the simultaneous equations in your CAS. So 3, 7, 1 instead. And saying you've got 3 equations, the variables are x, y, and z, and entering in your 3 equations. So 2 times x. As long as you answer the question sufficiently on paper, we can't control how you're actually getting your CAS to find the answer. Okay, 2 times x plus y plus 4 times z equals 17. My first equation, 3x minus y equals negative 3. You don't need to add in the 0z. And then x plus 4y plus 5z equals 7. And hopefully we get the same answers, which we do. Okay, so there's absolutely nothing to say that you couldn't use that method in your CAS to determine this final answer here. Okay, so it's up to you what you actually put in the CAS. We can't check that. but you do need to, in this case, set up and solve a matrix equation, set up a matrix equation, which is what you've done here, solve the matrix equation, which is what you've done here, and then obviously get your CAS to give you the answer. Okay, example 4. So here we need to actually generate the equations ourselves from a worded problem. Matteo and James scored 28 goals between them in a netball match. Matteo scored 8 more goals than James. If M is the number of scored by Matteo, and J is the number of goals scored by Matteo, and J is the number of goals scored by James, set up a pair of simultaneous equations involving M and J. Okay, so there's 2 bits of information that will allow us to make 2 equations. Matteo and James scored 28 goals between them. So Matteo's total goals plus James's total goals equals 28. Okay. The second bit of information is that Matteo scored 8 more goals than James. Be careful about this relationship. It's easy to misinterpret this algebraically. Sometimes people go, oh, M plus 8 equals J. But that equation is not correct because that's saying that James's score is Matteo's score plus 8, okay, which is not what the sentence says. The sentence says that Matteo scored 8 more goals than James. So Matteo's score is James's score plus 8. So be careful about that interpretation. Okay, then in part B we're going to want to write the equations from part A as a matrix equation. So we need to make sure that we've got everything lined up. We want to have a number times M plus a number times J equals a number for both equations. Okay, in order to get our matrix equation. So the first equation is fine. It's 1m plus 1j equals 28. No problem with that. But the second equation, we want to get the j on the left-hand side. Okay, so there's no problem with that in terms of format. This equation, I'm going to write this as m take away j is equal to 8. Same equation. So there's my other one. So now I've got my pair of equations. Okay, so I'm going to write them so you can see them lined up. Okay, so this is m plus j equals 28, and this is m minus j equals 8. Okay, so remember this is 1m plus 1j and 1m minus 1j, so thinking about your coefficients. So when you make the matrix equation, it's going to be 1, 1, 1, minus 1. Won't be xy this time because we're multiplying by m and j, so using variables consistent with the question. And that's going to be equal to 28, 8. Solve the matrix equation to find the number of goals scored by each player. So we know to solve this matrix equation, we're going to need to pre-multiply by the inverse of that. And so we can get our CAS to do that. Or we can get our CAS to just solve the simultaneous equations. We'll have no way of knowing in marking your test or exam. 1, 1, 1, negative 1 to the power of negative 1, so it's inverse of that, and then multiplying by 28, 8. And we get 18 and 10, and then make sure we answer the question. Solve the matrix equation to find the number of goals scored by each player. So we now can see that M, which is the number of goals scored by Matteo, is 18, and J, which is the number of goals scored by James, is 10. Okay, so therefore Matteo scored 18 goals, James scored 10 goals. Okay, final example. On Monday, Alex buys 3 coffees and 2 muffins from the local cafe and spends a total of $21.20. On Tuesday, Alex buys 2 coffees and 3 muffins from the same cafe, spending $22.80. If C is the cost of a coffee and M is the cost of a muffin, set up a pair of simultaneous equations and then use a matrix method to find the cost of a coffee and the cost of a muffin. Okay, so we've got 2 equations that are going to come from Monday's coffee buy will be one equation, and Tuesday's coffee buy will be the second equation. Okay, so on Monday he buys 3 coffees and 2 muffins. The cost of a coffee is $C. Okay, so 3 times C is how much he spends on coffees, plus he buys 2 muffins. So 2 times M, where M is the cost of a muffin, is the cost of the 2 muffins. And we know on Monday, so this is his Monday information, he spent a total of $21.20. On Tuesday, he bought 2 coffees, so 2 times the cost of a coffee, and 3 muffins, so 3 times the cost of a muffin, and he spent $22.80. Okay. Now, at this point, you can get your CAS to solve these simultaneous equations and you'll have the answer. But it does say use a matrix method, so we at the very least want to set up our matrix equation. So 3, 2, 2, 3 times CM, so make sure you list the letters in order, first letter and then the second letter, equals 2120, 2280. Okay, now we know that to solve this matrix equation, we need to multiply it by the inverse of that, and multiply that by 2120 and 2280. So we can get our CAS to work that out for us, and then we should be able to answer the question. So 2 by 2 matrix is 3, 2, 2, 3. We want the inverse of that, and we're going to multiply that by 2120 and 2280. Alright, we find we get 3.6. We're in money though, so I'll write 3.60 and 5.2, so 5.20. So therefore, the top row was coffees. So coffee was $3.60, muffin was $5.20. So therefore, each coffee cost $3.60. Each muffin cost $5.20. Okay, so 2 lots of work here today. Exercise 12B is just practicing sort of solving the simultaneous equations, and then the worksheet in Appendix D is some more worded problems where you actually need to generate the equations yourself first and then go on to solve them using a matrix method.